Uh, Good evening, everyone. Wish you all a happy new year. Um, it's a special pleasure teaching this course, Optimization and Machine Learning. It's a very happening area. It's also an area where I'm personally invested in several of my projects, and it's it's an area that has actually also created significant impact. And we'll see how that's the case as I progress. So I'm Ganesh Ramakrishnan, faculty member at the Department of Computer Science and Engineering. So let's look at the outline of what we'll discuss today. We'll first motivate why take this course, what are the prerequisites. Um, I must point out that for a very enthusiastic learner, these prerequisites are soft prerequisites. I won't impose any of them as hard prerequisites. Um, for example, linear algebra, algorithms, um, and machine learning. I would expect that if someone doesn't have the requisite backgrounds, the person will actually pick up. We have extensive set of references for almost every lecture. And if you go to the Moodle page right now, you will basically find, all my previous year's lectures I've put as samples along with the references. So we'll also go over a kind of course plan. The most important thing is logistics, and then talk about continuous optimization and discrete optimization machine learning, the two major limbs of this course. Okay, so why take this course? Um, Whether you like it or not, moment you have machine learning, and more so when you have big data, you need to optimize. You need to optimize on the use of computer resources. You need to optimize on the labeling process. You need to optimize on uh, the amount of computation and data that you use for tuning what we call hyperparameters. Optimization also there in scheduling and planning. Um, for example, in simple things like scheduling lectures, how do you make sure that the conflict between lectures is minimized, right? There could be obviously 24 hours and there will be some amount of conflict, but you want to minimize it, or rather satisfy as many constraints as possible in terms of student preferences of taking courses. Um, so operation research, control theory, there's been a lot of industry, new age industry for the six basically requires use of optimization and machine learning, control theory, data analysis. Especially the medical industry needs a lot of data analysis. And when I say data analysis, I don't mean just clinical data analysis, which is of spreadsheet records, but now we're talking about a lot of unstructured data as well, audio, visual clips, for example. In sometimes you also want to simulate data that um, can act adversarially to your machine learning algorithm. That notion of adversarial behavior of the simulated data is also characterized by optimization algorithms or optimization formulations. Search engines, right? How do you optimize uh, the advertisement, the use of the real estate, the search page? How should it be laid out? There is optimization, both discrete and continuous. Ranking, search result requires optimization. You could look at when you have a bunch of URLs. Let me give this specific example of search result optimization. So imagine you have a search engine page. Okay, let's say you have a search engine page. Um, and you have results, search results. Okay, R1, R2, and so on. RK. Now, what has optimization got to do here? The user might find these results in response to some query queue and might select two of these links, might browse two of these links with sufficient retention, since might go and read the page for a longer duration. Now given R2 and let's say this is RK have been preferred over the others, you want to now learn your features such that in the future the features, the uh, characteristics of those pages that made them rank over the others is given higher weightage. So basically what you want to do here is, let's say you have parameters to be optimized. You want to minimize some loss um, with respect to parameters W. Now what is this loss over? So I'm going to use this W as a prefix here. The loss is such that R1 and RK are preferred over the rest. I'll just call it rest here. Um, Now, how do you characterize the preference over the rest? You could do this using pairwise constraints. So L could be decomposed, for example, as LW summation over the rest. Okay, and let's use some indices in the rest. Okay, so let's say I have these index I in the rest. So I want weights W such that the result R1, the loss incurred by ranking R1 below. I'm trying to avoid too much math here, just simple textual description, R1 below I, right? And of course, I can now do this for RK below I. I'll copy this whole expression plus RK below I. Now this entire is basically a notion of pairwise. Okay. However, it may be that I really want R1 to be ranked higher than RK and the remaining pages to be ranked below RK. So I might want to also respect the mutual rank between R1 and RK. Okay. So while this is just pairwise loss, I could look at more sophisticated losses. Okay. This is called pairwise loss. I could look at more sophisticated losses. They're also called listwise losses. So let me use a different color and let me show the expression. We're beginning with very ambitious settings here. Okay. Um, the pairwise and listwise. I'll talk about a surrogate loss, which is or a cheaper loss, which might be much easier to solve than these. But these are real coveted losses. So again, I want to minimize the loss with respect to W such that the loss incurred by ranking R1 below RK, right? And then that below rest. Okay, now this requires more work. You may have to try all possible combinations, right? R1 below RK below rest. You can decompose as saying R1 below RK and RK below the rest, and so on. So list-wise loss is more complex. However, the two of these have a surrogate. The surrogate loss is just called a preference loss or just a classification loss. So, and those of you have done a simple logistic, right? You actually use a logistic loss. So what would that entail? Basically, that would entail that you're trying to look at minimum over W of the loss such that R1 is ranked has as a class 1, RK has 1, and the rest have zeros. So I'm going to just write this as vectors. A vector of zeros. 0 means they were not selected. Okay. And this can be actually decomposed. You don't have to now have this giant set of arguments. You could just say summation over I. All right. You could say I in rest of LW. Oh, of course, you need a minimization. Um, of I having label 0 plus the loss the loss associated with not having it 0 rather, um, and the loss with R1 and RK and so on, right? So for lack of space, I'm going to just, yeah. Okay, so this is our surrogate loss. Surrogate is basically an approximation, and surrogate will also use in the sense of often giving you an upper bound if you're trying to minimize. Okay. So this is an example of how optimization is everywhere. Now, optimization formulation itself is very tightly tied to the design of algorithms. As you can see here, you want to make the search of W for the search engine ranking loss feasible in reasonable time. It might not be a real time issue. You don't want to do this for every search query, but once in a while you may want to learn. So it should really happen in reasonable amount of time and so on. So the mathematical modeling is the process of defining and modeling the problem. That's what we try to do now. Mathematical modeling entails even writing down the exact expression for the LW in the gray case or the pink case or the green case based on which formulation we adapt. So the other is computational optimization. Once you have designed the problem, you need to identify algorithms to solve those optimization problems either optimally or near optimally. Now what happens is, let's take the example of the simple logistic loss. The simple logistic loss might not be the best loss we would have formulated for this problem, but it can be solved optimally or nearly optimally, given some interesting convexity properties it has. But it, for all practical purposes, it is optimally. On the other hand, something like um, the listwise loss, I mean, even solving nearly optimally requires some assumptions. Whereas if you consider the pairwise loss, the one in gray, yes, you can get close enough to the optimal solution. In fact, we'll see um, uh, there's a special class of linear optimization problems which have this total unimodularity property where, and you can have these pairwise constraints reflected through edges in a massive graph, and you're trying to find some um, best possible configuration of the nodes, right? So you can do that nearly optimally. There are some greedy algorithms. So this is an example. The listwise loss might possibly um, qualify to be solved nearly optimally. This is an example. Please do feel free to interrupt at any point of time. Um, you don't have to even raise your hand, but yes, if you post queries, I'll keep checking once in a while. I would like this to be a lot more interactive. Um, if there are questions, I'm just going to take them here. So this is a second perspective, the computational optimization perspective. And it turns out that machine learning and AI, which are ubiquitous, they at the core require solving such optimization problems. They require both mathematical modeling and designing computational algorithms for solving those optimization problems. And some of us might wonder, do we really need to understand optimization algorithms? Because with a few lines of code in PyTorch or even TensorFlow, you can write ML applications, you can compose networks together. However, you need to appreciate that uh, you can be good consumers of machine learning by using PyTorch and being somewhat indifferent to the underlying optimization algorithm. But if you want to design or extend libraries in PyTorch, add a new libraries, solve real world problems, being an engineer who just consumes existing optimization algorithms is far from sufficient. So the open source libraries today that offer capabilities to build products with practically zero knowledge of ML, these capabilities are somewhat limited by the previous use cases. These libraries have been built keeping some previous use cases in mind. They were for a long time people were looking at image classification, but then object detection became important. You don't want to just classify an image, you want to identify objects. But now you don't want to just identify objects or humans, you want to identify their poses. You want to get depth information. So as the needs increase, obviously the libraries have to be expanded. So to push the boundaries of research, this is the key. To push the boundaries of research and solve real problems, you need to gain hands-on experience in ML, and going beyond that, hands-on experience in the optimization algorithms that underlie solving ML models.
Hello.
Yes, please.
Yeah, sir, this is Vishesh. Sorry to interrupt, but I have a
Please go
question
ahead. Yes.
that why we always prefer Python over other languages when it comes to machine learning?
There's no specific reason to persist with Python when you build when you solve real world problems, when you build systems, but prototyping becomes much easier. So Python, its predecessors, Perl, and maybe to some extent Java. The Java also gets used in real time systems. These are more amenable to prototypes. We quickly build together models because they have some interesting properties. uh, I mean, like Java was always preferred because it's interpreted. You don't need a you don't need an entire ecosystem of compilation, etc., to be set up in every new virtual machine. But basically, a virtual machine provides you the abstraction, right? So Python has a similar kind of advantage that Java leveraged. But I must tell you that our being fascinated with Python is only because it just offers a very strong starting point for prototyping, quick experimentation. Is that okay? Otherwise, there are separate courses on
Oh,
programming languages which explain the characteristics of Python and PyTorch. Um, and yeah, we will, of course, we'll also use PyTorch extensively in this course.
okay, sir.
Proceed. Yeah, thanks. So yeah, the key is optimization is one of the important backbones of machine learning. There's a B missing out there. Yeah. Okay. So why take this course? As I already demonstrated, statistics are very important if you're going to basically design your loss function for ranking, whether it's list or pair, list-wise or pair-wise, or just simple classification. You need the statistics from the ranking to be availed in the loss function. So that's key. And the modeling itself is also driven by statistics. However, you put them together through optimization, as we saw the L1, L2, the three losses we saw. Matrix algebra plays a very important role. Now, if you were to try and solve, the algorithms invariably would invoke matrix algebra. Okay, so let me tell you where statistics comes. Statistics comes basically largely in modeling, whereas matrix algebra plays a key role in designing the optimization algorithm itself. Often it also comes the design of the optimization algorithm or the reformulating the optimization problem. And the simplest example is that if you're looking at ax minus b norm, this is linear algebra, right? Minimizing ax minus b norm square. Now, if you were to transform the variables x into some space y, right? How would the solution change? Basically, we are saying that if you had a rotation of the coordinates, would the previous solution need to be discarded to discover the new solution? Well, no, matrix algebra can come to rescue there. So you can come to rescue, for example, to um, add up the solution to x minus b square to say a tilde x minus b square, a small change in a, or there's a change of coordinate system for x. So solving under coordinate change. Or transformations. And these transformations, as long as they're linear, then you're more or less um, hopeful of finding matrix algebra, linear algebra based tricks that can help you transform solutions as well. This is an example. So I'm just looking out for questions. If there are, please do post them on the chat. So why take this course? As I said, optimization is one of the pillars of ML. Now, continuous optimization, the simplest example being classification. Let me just copy this example here. The simple logistic loss. Now, this is often the loss that you might see is the cross entropy loss. Very well known cross entropy loss. If you're not familiar, that's okay. But the idea in the logistic loss is that it's after all a relaxation. Okay, it's a relaxation of a discrete optimization loss or a discrete optimization problem. What's that relaxation? Well, you could think of this relaxation as a relaxation of the pairwise or even listwise losses. That's one way. And you might, in fact, the listwise loss, you can increasingly see the combinatorial nature coming up. Right? So the one perspective is, and that's the reason I'm giving this example. So, so it's a relaxation of the listwise loss, or a relaxation. But there could be multiple other relaxations. Okay, so you basically say you have tried to relax the constraint between R1 and RK. In fact, if you have R1 equals 1, RK equals 1, and rest equals 0, you're not solving R1 below RK. Right? So if you want to adhere to that as well, you'll probably need ordinal regression rather than just classification. You may need R1 equals 5, RK equals 3, and the rest is 0, or some sorting of numbers that obey such an inequality, series of inequalities. So it is example of a relaxation of listwise loss. Okay. So in general, classification itself is a relaxation. The classification losses. However, you may say I'm going to solve the original problem, the discrete optimization problem. For example, the listwise loss. These occur in inference problems in structured spaces, learning problems, and also auxiliary problems like feature selection. What is the right subset of features that I should use to build my classifier? What is the right set of points I must use from my large data set such that the set of points gives me nearly the same performance as the entire data collection? I want a summary of a bunch of images or a bunch of documents, or I want to search across multiple architectures. I'm just not going to take examples from all, but some of them I'll illustrate. So let's look at architecture search. So there are multiple aspects to the architecture search. Um, one could be just whether to add an additional layer or not. Okay, so let's look at this neural network. Okay, not necessarily a fully connected network, and let's assume for the amount of time that there's one such network, simple network, but there's another network which has an additional layer. Now, how many layers should I keep adding? When should I stop? Okay, so sorry, you have added one layer. Okay, so this you could think of the edges here as forming random variables connecting the nodes. So choice or inclusion of an edge leads to the random variable um, corresponding to that edge being set to 1, else it's a 0. Okay, so you could think of this architecture search over a large number of edges, determining the right subset of edges as basically assignment of 1 and 0 to the existent or included and non-included edges. Okay, so for example, this edge didn't this edge isn't there, so this is basically 0 or its value is 0. You could also have the architecture search with respect to addition of layers. So an entire layer could be set to 0 or 1, which means it could be included or not. But you could also have the kinds of activations as a third choice, a third possibility. Let me just copy this entire network to bring out a third possibility. Okay, so here my possibility is not 0, 1. And what I'm interested here in is what are the activations here? Is it a ReLU? Is it TANH? Sigmoid and so on. So that's also part of architecture search. So you can see this is all discrete optimization. Okay, there's a question, Harshraj. In the time of auto derivation and various libraries like PyTorch, where we can define any kind of non-convex laws, how does studying conventional optimization help when it may not solve non-convex functions? Okay, so interesting. I'll come to that. Just give me some time. But mm, the strongest example I can provide is the discrete optimization. The libraries offer solvers which are largely continuous. Okay, and people are increasingly getting interested in solving the true problem without its relaxation, in which case you're trying to address the discrete optimization problem. And for discrete optimization, I must tell you that there aren't so many solvers. So why don't you look at I'll be, in fact, I'll be showing you our platform as well called Decile. But one of my students, for example, PhD students, he's put together this entire library called submodularity. That isn't a standard library that is available with PyTorch or any Python existing state-of-the-art ML model. So I'll just send you the link. You're welcome to explore. Um, called submodularity. So all this, by the way, is just over the last 1 year or so. So it isn't that this was added long back. Okay. In general, if you look at our platform called Decile, Data Efficient Machine Learning, you'll find a whole bunch of other. In fact, submodularity itself is a part of Decile, Data Efficient Machine Learning package. Okay. And most of the work in data efficient learning is about posing the right optimization problems and solving them efficiently. So Harsh, I'll try and address your question further later on, but I hope it's okay for the time being. Harsh. Okay. I'm assuming. Okay, thanks for acknowledging. But I'll see. We'll show a lot more examples. Um, okay, I'm going to proceed. In fact, I must say that most of um, the decile.org and submodlib are about not just discrete, but a mixture of discrete and continuous optimization problem. So you want to do clustering of data points and then learn models for each cluster, right? So clustering becomes a discrete optimization problem. Feature selection is a discrete optimization problem. But imagine you want to do feature selection and learn a model on the subset of features, or network architecture search in conjunction with learning the parameters of the network. So that would be the a canonical example building on what we discussed in the previous slide. This is in conjunction with learning parameters.
Sir, can you explain how clustering is example of mixed continuous and discrete optimization?
No, no, clustering is not. I'm saying if you wanted to do clustering followed by learning models specific to each cluster, that would be an example of mixed, discrete, and continuous optimization. Right. Now, clustering could also have the continuous optimization angle if you're trying to learn weights associated with the cluster points. Okay. So often you want to cluster the points together and maybe give differential weights to different clusters. So there are lots of applications around clustering which involve mixed continuous and discrete optimization, though most traditional treatments to clustering are in the form of discrete optimization problems. As it's exactly in the spirit of what I said, combining clustering with other applications.
Okay, sir. Got it.
Thanks.
Thank you.
Okay, so again, this slide is alluding to what was pointed out earlier by Harsh Raj. Right, there are countless numbers of ML libraries available which implement all kinds of optimization algorithms: TensorFlow, PyTorch, Psi, sklearn, Opal Wabbit, if in case you've used it. So one is, yes, even if they exist, we want to pay them the complete homage. You can look at these algorithms, their implementations, understand how they work, why they work, how fast they work. Right? So that's certainly catering to the need of understanding how they work. I mean, in as much as why would you learn about deep learning if most deep learning models have already been implemented, because you want to make the best use of those models. So even if you want to make use of TensorFlow or PyTorch optimizers, inbuilt optimizers, you would need to know what are learning rates. You need to know what stopping criteria are desirable in different settings. Okay, so as a kind of addendum to this, um, yeah, and develop insights into learning rates, and the learning rates, the dynamics of learning rates. Um, as I said, network architecture search is a huge area. So I'll put NAS, the short form of that. And even the choice of the optimizer. So some optimization algorithms are fast, but they don't behave very optimally. Right? Some are slow, but they give optimal solutions. Now, what is the right trade-off I should be seeking? Okay, trade-off between speed and accuracy, and by by the choice between the or choices between the optimization algorithm. Okay, so that's one. But the other is that invariably in research you'll come up with new optimization problems, and that's what I was trying to answer in response to Harsh's question earlier. Most often that's what happens. You might need to implement custom algorithms or at least a loss function. I'm going to give you examples from our own projects. For example, if you look at our work called on video surveillance, um, now these are this was part of the requirement from the National Center for Excellence in Technology for Internal Security. I'll send the link here. You're also free to go and visit this site. Um, so video surveillance analytics. Now imagine that you have crowd counting models. Okay, crowd counting models that have been trained on Chinese data sets in US settings. Now when you deploy them in Indian settings, they don't work as well. So you might say, well, let's collect data in the Indian setting. Now, it's a painful exercise collecting data. If collecting data was so easy, you'd probably have lots of Indian data sets on crowd counting. That's not the case. And what we have built are products for Indian settings, video surveillance in Indian settings. Now that's possible because we did some smart subset selection. We identified a target setting where these models need to be trained. Okay. The subset of we identified smartly the subset of data set that should be annotated. and that to a small subset. Okay, the small subset of annotated that should be annotated such that it complements well um, the existing data sets. So when it comes to actual deployment, um, you will come up with new optimization problems. So you look at our latest AAA 2022 work, where it's called Trust Targeted Subset Selection, exactly dealing with this issue. Okay, it's called Prism. Okay. So these are grown from real applications. Most of our papers for the last couple of years are really driven by real world problems. Okay. Even if you don't implement new algorithms, you'll at least have a better idea of which algorithm to use in which scenario. I mentioned this earlier. It's a repetition, but it's very critical. Okay. So any questions on this? Why take this course? So the philosophy of this course is that theory is basically only the first term of the Taylor series of practice, right? So if you have a Taylor series of practice, you begin with theory, the first term, but then the rest, what, how many terms of approximation should you actually retain if you know Taylor series expansion? That really comes from practice. So uh, the focus will be on the algorithmic aspects of optimization, but not so much on the modeling. In fact, uh, in the last offering of this course, I did spend a little bit more time than I would have liked on modeling. But in this course, we'll try and increase the breadth significantly. So we'll give a flavor of the proofs and proof techniques, but we'll not try to make this course heavily theoretical. But um, at least there'll be a couple of proofs which you should understand thoroughly. It's not that you have to understand the proof of convergence of every algorithm that we presented, but some of them should be taken to the logical conclusion, so that you develop the rigorous habit, right, of basically making sure that an algorithm that gets designed or proposed um, is sound in the sense that it'll actually converge to what it's meant to optimize. Okay, so do develop a habit of analyzing at least some algorithms, though I won't spend all the time in the course itself. When I say analyzing some algorithms for convergence, you have two things: the convergence and rate of convergence. Convergence is to the objective, and rate of convergence, how fast you converge to the objective. So I'll be giving some examples, but I'll be also delegating some of it to additional reading, so that we don't spend the valuable time of the class just studying convergence. We'll also focus extensively on implementational aspects. There'll be two assignments, and we'll implement mainly ML loss functions and algorithms. Okay. So I would like to hear from you why you are taking this course, what you expect from this course. Some of you. Somebody had raised hand. Okay. I'll wait for a few more seconds. So your speaking up will really help me.
Yeah, I am taking this course for understanding the submodularity and alpha submodularity. The discussions are going on like when we are explaining, reading any paper and the discussion of our MTP work. So
Okay. Thanks. Really appreciate this. Um, okay.
So yeah, I'm taking this course mainly because this would give a flavor of the studies of algorithms and the analysis of algorithms, and it would help us basically choose the right algorithm at the right point.
Study of algorithms for more informed choices. Thanks. Any other reason? Okay. Few more seconds. So there looks like there will be interest in discrete optimization. I'm happy because I'm going to spend more time on discrete optimization compared to last offering. Um, okay. So here are some prerequisites. Basic linear algebra, matrices, vectors. They'll come up all the time. So the onus is really on you. If you haven't done a basic linear algebra course, you'll have to pick up, spend that additional time becoming familiar. Otherwise, we'll not be able to make significant progress. Again, basics of machine learning. It's ideal that you have taken a UG course or a graduate ML course, but if you haven't, I won't stop you from attending this course. But again, it's your responsibility to pick up. It'll not look good if the class gets held up because one student is not completely conversant, or not even conversant, has not even brushed up some basic ML concept. It's not that we're going to do everything in machine learning, um, but yes, there'll be key concepts that will be brought up again and again. Algorithms course, again, if you've done an UG or graduate version, great. If you haven't, you need to pick up you need at least the relevant parts. I mean, if there's some dynamic programming somewhere, a greedy algorithm being talked about somewhere, and so on. Okay. The first half of this course will be about continuous optimization. We'll run through basics of continuous optimization. Some of it I'm going to just give it as no, homework reading or homework brush up. So I have the recording, fortunately, of the previous year. Some of it will, some of the recordings from previous year will actually offer as brush up. In fact, there are recordings of pretty much almost 3 or 4 years. So the previous year I taught optimization and machine learning, but in the past I've also taught convex optimization. That would also be helpful. And again, I'm not going to spend all the time, going to too much of theory, because convexity itself is a huge space. That the notion of sets versus functions, right? The set perspective on functions, the function perspective on set, all that I'm not going to go into details here. So wherever required, I'll allude to them. The focus here will be more of intuition. We'll make sure that you get the intuition and you have the required tools to deal with the intuition, but the proofs behind some of those tools, which could be theorems, are going to be left to previous year recordings. So let me make a point, especially theorems. I mean, there's a very famous theorem called separation theorem. No, I don't want to spend my time proving a separation theorem, but yes, that will be treated as a black box. Uh, so especially fundamental theorems that have benefited optimization algorithms. So this is hyperplane, separating hyperplane. In fact, there are lots of equivalent conditions for convexity, equivalent conditions for Lipschitz continuity. I'm not going to proving each of those equivalence conditions. Some of I might, for giving you a glimpse, right? So this is just giving examples of equivalent conditions for convexity, or likewise. Sorry, what did I do? Somehow move to the last slide. Okay. Yeah. So these are going to be through largely previous years recordings. So the statement itself, I'll make it very clear and explain intuitively, geometrically. So that holds largely for basics of continuous optimization, convexity, gradient descent. I'll spend a lot more time on projected proximal gradient descent, subgradient descent, and all its variants, accelerated gradient descent. Again, now duality is something that can take up half a course or even more actually. And the different notions of duality, Lagrange, Fenchel. So instead of trying to prove in them in details, I'll refer you to proofs. Wherever intuitive ideas can be provided geometrically, algebraically, I'll do that. So again, I would say duality, the focus will be more on the intuition. But it will not be intuition to the extent of just saying okay, plug in Lagrange multipliers. It'll be more than that. It's slightly deeper than just what you might get in a machine learning course, significantly deeper, but not a rigorous proof, right? But yeah, coarse and shallower than a convex optimization course. So that's so somewhere in between. That's how a treatment to duality, for example, is going to be. Um, okay, we are probably running out of time. I'll and likewise we'll do coordinate descent, Frank Wolf, which is second order methods and optimization practice. The second half of this course is going to be about discrete optimization. I'll see how many of them we can cover. Being quite ambitious. But certainly what I want to spend significant time on is submodularity, submodular functions, submodularity and convexity, submodular minimization, submodular maximization. So minimization we'll spend relatively less time, maximization more time, but the basic tools we'll be providing, right? And then we'll see connections of some of these problems also with matroids, with spanning trees. In fact, matroids are very fundamental. You can teach a course on submodel optimization without referring to matroids, but the fact is that the notion of matroids, polymatroid functions are foundational to submodular functions. Okay, polymatroid rank functions. So there are a whole bunch of other, ST pass, ST cuts, which also turn out to be sometimes special cases of submodular functions. So from that perspective, the submodular functions will actually give you a larger um, uh, template in which you can cover some of these specific formulations and algorithms. I'll be really happy if I get time for optimal transport, but for me that's a low priority. So these are some relevant books for this course. Um, the optimization, convex optimization book by Sebastian Bubak is very good. Now we say convex everywhere, but you must note that very often we are talking about convex regions of functions. It's not necessarily about the function being convex everywhere. Okay, so the word convex should not make you think that this kind of course or use of convexity limits us. In fact, use of convexity is liberating because we are often looking at convex regions, even of non-convex functions. And lots of convergence analysis is about local convergence because the local convergence is localized in the convex regions. Okay, so therefore the word convex can be understood from that perspective. Somebody had a question? Yeah, then there's a nice, I would say, extended journal article, but it's almost like a booklet, if I may use that, by Francis Bach, Learning with Submodular Functions. It's available. Most of these are actually available online. I have uploaded all of them on Moodle, most of these on Moodle already. Okay, and some of these are more like Fujishike's book is very foundational. We might refer to sections, but that book won't be required to be read in details. Okay, there's plenty of good references, is what I want to say. Right, and just as a recap, continuous optimization in machine learning um, is often as relaxation of empirical risk minimization. And you must have seen logistic regression, least squares. If you haven't, we'll be alluding to them. Support vector machines. These are all supervised learning problems, but even unsupervised learning is based on optimization formulations. And we'll give examples from contextual bandits and reinforcement learning, the softmax estimators and policy exponential methods as instantiations of optimization. And finally, recommender systems, matrix completion, we give those examples as well. Not necessarily convex, but continuous optimization. So this is a big picture, the types of optimization problems, something that you can carry home. Okay, so you have mixed, continuous and discrete optimization as a real larger class of problems. Within that envelope, you have something called continuous optimization, That's a subset. Got muted. Um, the continuous optimization space is a relaxation often of the discrete optimization set of problems, but they're largely complementary and to some extent also disjoint. Now it turns out that there's this interesting class of optimization, which is a subclass of continuous optimization, and that is an analog in discrete optimization space. So what you find about convexity often holds for submodularity as well, and that's something we'll deal with later on. Convex minimization is possible, in a computationally friendly manner, right? The submodular functions, on the other hand, they're they look more like convex functions, but when it comes to minimizing, they behave like convex functions. Very interesting. So submodular functions have this kind of shape. They are diminishing returns. So diminishing returns like concave functions. However, efficient to minimize like convex functions. However, they also have an interesting property. They can be somewhat efficient, not exactly, but somewhat efficient to maximize as well, uh, through approximation algorithms, not exact algorithms, not exact optimization, but through approximation algos. Okay, so that's one reason why we kind of single out, submodular problems and convex problems, and therefore it becomes interesting to also understand convexity. In fact, there's this very famous Loa's theorem by which you can you see a stronger connection between submodular minimization and convex optimization. Okay, there's Loa's extension and the corresponding theorem. And here are some examples. So you've seen SVMs, logistic, least square, all of them yield themselves to convex optimization. Some of them, like these squares, also are quadratic. Large class of deep neural networks is about non-convex optimization, but they do benefit from algorithms developed for convex optimization. On the other hand, the examples of submodular optimization are like facility location, set cover, graph cut, mutual information, entropy minimization, and so on. In fact, maximization as well. But there are also linear cost problems, which happen to be a specific subset of submodular optimization. Okay, so now coming to logistics and grading, the important part. So the credit and audit requirements are as follows: 20% mid-semester exam, 30% end sem. There'll be a 20% project, which will be largely about implementing any related paper into implement algorithms in the paper. You can do a basic performance study, diagnose the performance. However, I would expect projects to do something more than that, suggest ideas for improvements. A more advanced project would basically take a problem specification for which there's no solution and actually suggest something, implement a solution and suggest something. Even if that doesn't perform great, a good analysis would be very helpful. There'll be 10% for reading and paper presentation, and 20% will be split across 2 programming assignments. Okay, so as I had promised earlier, this is going to be a lot more hands-on course, though the classes would be intuition and some theory. The evaluation 50% is through actual understanding of implementations, applications of optimization, and so on. So we'll have these lectures in slot 8, Mondays and Thursdays, 2 to 3:30 p.m. Lectures will be on MS Teams, and you kindly join this MS Teams with code 04HT07Z. They'll be recorded. They'll all be organized on Moodle. Durga Shivasubramaniam will be the TA as of now. We'll probably have more based on the registration is. Then audit students need to undertake the project and paper presentation and do them well. So they can be exempted from mid-sem, end-sem, and basically a programming assignment. They need to do the project and the reading and paper discussion. Okay, so these two. So here are some course project ideas. I'll spend a lot more time later on, but what I'm excited about is, we have actually my students teams have actually left a lot of legacy on which you can build. So we have this data efficient machine learning Python toolkit. In fact, the previous offering of the course, students came up with very interesting projects, some of them which are actually continuing and culminating into paper submissions. Um, so you can add components to it based on several discrete and continuous loss functions or optimization algorithms with wrappers um, in machine learning. For example, classification, recommender systems, etc. And here are some recent applications of Decile. As I already mentioned, we have this work on video surveillance analytics, which has heavily benefited from the use of Decile. Specifically, is this called submodularity, which I also posted, the submodel optimization. And we have a machine translation project which involves a end-to-end ecosystem where the models can learn, where the post editor improves with the user edits. That's largely because of lots of use of Decile. And likewise, we have an OCR work. Couple of my students have worked on knowledge distillation. Some are working on federated learning, subset selection for crowd counting. I gave that example earlier. Targeted subset selection for speech. Imagine that you have lots of well-trained speech models, but you want to do them, have them do well in Indian speech, Indian accented English. Tamil accented English could be very different from Hindi accented English. So how do you adapt them? So I think Amazon has a very recent call for proposals exactly in the space of targeted subset selection for speech. So we've been working on that. We can discuss more ideas as the class progresses. So a lot of exciting things we can do. As far as Decile itself is concerned, this data efficient machine learning that's abbreviated as Decile. This is meant for principled human machine interaction for machine learning, and it has these 5 components: submodel, the submodel optimization, efficient and scalable library for submodular optimization. And then there are others which actually also build on submodel and other aspects of machine of optimization. One is distilled, deep diversified interactive learning, CORDS, which is for core sets and data subset selection, SPEAR, which is for semi-supervised data programming, and TRUST for targeted subset selection. So I gave an overview presentation of Decile as part of this Faculty Unplugged seminar series last semester. So it's on YouTube. So this could be another interesting aspect of what you could do for projects. So I think I've covered the course project assignment, logistics, etc. And I just can quickly run you through some of these applications that have really benefited from optimization. So in case you were wondering why do we need to study optimization, all of this basically, this was work on I presented. This has actually benefited from data subset selection and mixture of discrete and continuous optimization. I work on OCR, work on human in the loop machine learning for ecosystem for machine translation, and all this is through this platform called Decile. This is in close collaboration with my good friend and long-time collaborator Rishabh Iyer, who's at UT Dallas. He's also an IT Bombay graduate, and you're welcome to go through the site yourself. So it has all these components, and yes, you could have more components that you contribute. You could also have application of these components. So that will be about projects. As far as the Moodle page is concerned, I have actually organized it already by importing select content, basically especially the lectures slides from previous year. I'll hide them soon, but this is to give you an idea of what took place last year. There's already a playlist, a YouTube playlist where you can access these video lectures. I'll post slides for each lecture beforehand so that you have the you have an idea of what's going to be covered. Yeah, and lot of references have been put up together. So I have my own notes on basics of convex optimization. There's a warm-up ML book, The Elements of Statistical Learning, which I find the machine learning book which does the most justice to optimization, right? Most others just brush optimization under the carpet, but by Tipsy and Hasti and Tipsy Rani, sorry. And then there's a book by Lange, First Order and Stochastic Optimization Methods for Machine Learning. A whole bunch of other books that I keep referring to will come up down. So yeah, the convex optimization textbook. I also keep putting notes like notes on Lipschitz algebra, Sebastian Bubek's monograph on convex optimization, and so on. And the submodular part also has a bunch of references. So any questions or any pending concerns? So the question was projects will be in groups. Max size I will entertain is 3. I would recommend 2. I've generally found that when teams expand beyond 2, then it's effectively only 2 members who are contributing. So I would encourage 2 if you really want to learn. I typically assume that all members contribute equally. So from that perspective, it also help if you keep 2 for fairness sake. Any other question? Hope this answers some of your questions. Okay. So hope to see you. See lots of you taking up this course, taking it very seriously. And I mean, whoever takes this course, please feel the excitement that optimization is there to stay. It could borrow benefit from convexity. It could borrow from and benefit from submodularity and other well-studied areas of discrete optimization. But without optimization, you really can't push the frontiers of machine learning. So with that strong conviction, I would like to conclude. If there are more questions, I can take them. But we'll conclude the official introductory course. Thanks for your attention.